All right, so today we're going to look at limits at infinity, and we're actually going to tie this to something we did near the beginning of the year, okay? So be thinking about that and see if you can't figure out what it is this relates to before we even get there, okay? So first of all, thinking about limits at infinity, what are we talking about first of all? Well, we're talking about limits as x is approaching positive infinity or negative infinity. In other words, on your graph, we're either looking all the way this way to where x is positive infinity, or we're looking, what is our graph approaching as we go to the left to negative infinity, okay? Sometimes these are called a limit to the left or a limit to the right. Okay, I don't use that term real often because it's easy to confuse that with a left-hand or a right-hand limit, which is something totally different, as you guys know already. All right, but these are x's as we go to negative infinity or positive infinity. So let's look at some basic rules, and most of these rules are most significant here when we're talking about rational functions. If you just think logically about functions that are not rational functions, a lot of those they just kind of make sense and you can figure them out pretty easily. We'll look at some of those too, but most of these rules that we're looking at apply specifically to rational functions. The first of these is, if the degree of the numerator is bigger than the degree of the denominator, the limit approaches positive or negative infinity. Okay? Now, this is the case, we talked about this before, this is a case where if our limit is going on and on forever towards positive infinity or towards negative infinity, some, including your textbook, say then that the limit does not exist. Okay, I would take either result. Okay, but let's look at an example where we might see this. Okay, let's say we have the limit as x approaches infinity of x cubed plus 5x squared minus 3x plus 4. Now, if I just stop right there, what is the denominator?
1.
1. Okay. So, is the degree of my numerator greater than the degree of my denominator?
Yeah.
Yes. Okay. So, you can kind of think in terms of this. Any polynomial function, what's the limit going to be as we approach infinity or negative infinity? If it's not a rational function, it's just something like this, then the limit will equal infinity or negative infinity. How can we tell which one it's going to be?
Based on whether it's positive or negative on the highest degree.
Okay, you guys remember that leading coefficient test? Way back in chapter 2? Here we have an odd degree, and our leading coefficient is positive, right? So what does that mean?
Positive infinity.
Yeah, it's gonna start down, do something in the middle, and then continue up forever. Okay? So our leading coefficient test. So the limit as x approaches infinity of this will be positive infinity. Okay? Now, let's say we put this in a rational function. In order to apply to this rule, what would have to be true about our denominator?
It would have to be less than to the power of 3.
That's right. X would have to have a power less than 3. So I could have x squared or just an x, or I could have just plain numbers there because the degree would be 0. All right. But as long as I have a power less than 3, I could have x squared plus 4x, plus 5. We would handle that the same way that we would how we saw it originally. Okay? Now, why is this? It's kind of an interesting idea. Because if you think about it, I mean, here we'd have infinity squared in our denominator. That's pretty big, right?
Mhm.
But how big is infinity squared compared to infinity cubed?
Small.
It's pretty small. And we're getting into some things that'll kind of blow your mind if you think about them too hard.
Aren't they the same?
Well, they are, but it's what we call degrees of infinity. If you study number theory later on in college or whatever, you get into some advanced level classes, you'll talk about degrees of infinity. I mean, think about it. How many integers are there?
Infinite.
Infinite. Okay? How many odd integers are there?
Infinite.
Infinite. Half infinity,
Yeah.
right? Half of the infinite number of integers are odd. Okay? Well, let's go the other way. There's an infinite number of integers. How many real numbers are between just 0 and 1? Infinite. Alright? See how kind of degrees of infinity works? Yes, we recognize that these values are infinite, but this one we recognize has to be more infinite, bigger than the other one. Alright, anyways, the idea is this. Because this is infinity cubed, so to speak, this is getting larger faster than our denominator is. Okay? And as a result, we end up continuing to go upward. Quickly, we approach positive infinity. Okay? And like we said before, we could also say that the limit does not exist. In fact, the book will say the limit does not exist because infinity is not actually a value. And in technical terms, a limit has to approach a value. Okay? So that's one rule. If the limit or the degree in the numerator is bigger, then the limit approaches positive or negative infinity. Second rule. If the degree of the denominator is bigger, what's going to happen?
Negative infinity.
No, it would have no 0 but not get to 0.
Okay. If the degree of the denominator is bigger, the limit's going to approach a 0. Let's think about this.
0 and
Okay. We're approaching infinity. We've got, let's just flip what we had up here. X squared plus 4x plus 5 over, what happened right there? Over x cubed plus 5x squared minus 3x plus 4. You'll notice here that even though we're squaring infinity, okay, the denominator is getting huge. Alright? So we are dividing by a larger and larger and larger number. Okay? And you say, well, the numerator is getting larger too. Yes, but the denominator is getting larger faster. Okay? So since the denominator is getting larger faster, what's going to happen with this is it going to approach 0 like this. Okay? What do we call that, by the way? An asymptote. Okay? So our limit approaches 0. So we have the numerator with a higher degree, the denominator with a higher degree. What's the only other possibility?
Same degree.
Same degree. What do you think we do there?
Straight line. No,
Could
not
be,
Well, if they're coefficient in front,
The degrees are the same, what do you say?
if the coefficient, whichever one is bigger.
Okay, it has to do with the coefficients. We're gonna actually take the ratio of the leading coefficients.
Oh, we did that before.
When did we do this before?
Chapter.
Chapter 2 when we were finding,
Holes. No, not holes.
not holes,
Asymptotes.
what?
Asymptotes.
Asymptotes, which kind of asymptotes?
Vertical.
Horizontal.
Horizontal asymptotes, that's right, okay? Horizontal asymptotes, well, I'll show it to you, okay? Horizontal asymptotes, the higher degree in the numerator, we had no asymptote, right? Higher degree in the denominator, the asymptote was at the x-axis, right?
Yeah.
So it was 0. If we had equal degrees, then we took the ratio of the leading coefficients. Well, really what we were doing, guys, is we were finding the limit as x approached infinity or negative infinity. Okay? So, now, let's just look at one like this. Let's say we've got a 5x cubed minus 4x squared plus this, okay? And then we have a 3x cubed plus 1 in our denominator, okay? As x gets larger and larger and larger, what is our limit going to approach?
5/3.
5/3. And you might say, well, what about this? I mean, this has, a plus 1 million.
That just moves it up.
Okay. Compared to infinity cubed, 1 million is nothing. Alright? So really what ends up happening is we don't care what all this is. That in the end is insignificant. Okay? I mean, it's kind of like it's kind of a matter of perspective. All right, you may say $20 is a somewhat significant amount of money, or $100 is a significant amount of money. All right, but if you're a multi-million-dollar corporation, $100 is nothing. Okay, that's kind of where we're at here. The rest of these functions don't even matter because the 5x cubed and the 3x cubed are so enormous. All of this is nothing.
What if you had it at plus infinity instead of plus 1 million?
Well,
Still doesn't matter because
you wouldn't have a
cube.
function. That wouldn't be a function. So, all right. So, now. The one variation I will warn you with is be careful when part of the function is a rational function and part is not. Okay, so for example, let's say we were finding the limit as x approaches infinity of, let's say, 3 plus x squared plus 4x plus 5 over 3x squared minus 2x plus 1. Okay? If we're finding the limit of that function, rule, okay, but what did we say about the limit of a sum?
It was the limits of the two parts, the sum of the two parts.
Yeah, it's the sum of the limits. So what's the limit of a constant? 3. It's the constant. So this is 3 plus
1/3.
the 1/3. Okay? The degrees are the same, so it's 1 over 3. Okay? So 3 1/3. Alright, so do be careful about some variations like that. Okay. But the rule would still apply. The rule can be used within another problem. Okay? Alright, let's try a couple here. Okay? Try these on your own here. See if you can come up with a solution.
Because he kept like, can we go over it like 50 times? Probably what it was.
So for the third one, you have to make it rational before you can do that?
No, I don't.
What is the approach?
You can just do it right away, can't you?
Square
Well, it's 1.
Would 3 be 3 over 2?
No, 1.
No.
I know. Think it through and just come up with an answer. We'll see what you guys all come up with.
Hardest one is last one.
Alright, let's think it through. Okay?
Tried rationalizing it, but it doesn't.
Yeah.
But then they're both to the degree of 100.
That's what I did.
Yeah.
I thought it was
Okay. Let's start with the first one here. What'd you get for the first one?
There's not even 0.
0. This higher degree's in the denominator, so it's going to approach 0. Okay. The second one,
3 7.
3 sevenths. The degrees are the same. Okay. Yeah, the big question here is on the third one. What's the degree in the numerator?
1/2.
A half. What's the degree in the denominator?
Half minus 1.
The degree
1/2. So
is a half, right? Yeah, there's a minus 1 in there, but when you're thinking in terms of degree, they both have a degree of 1/2, right? And as you get bigger and bigger, does this 1 really matter?
No.
No. So, this one, the limit will equal 3 over 2. Okay? And our last one. Anyone come up with an answer? 1. Okay. I heard 1, I heard infinity. Any other possibilities?
一对100次方式的还是
但是
你无从大而说那个
Doesn't exist?
Oh wait, 1 plus, oh, 1 plus 1.
Let's,
相当于1加0。
Hugh, how did you come up with 1?
This is doesn't matter. It's 1 of x if x is an infinity. So that is like it will be near to the 0. So it's 1 plus 0 and times x
It's 1 plus 0.
times x and x is infinity. So it's 1 of 100, 1 of 1000, and 1 of anything is 1. So it's 1.
That's right. Okay. So, here we go. As x is getting huge, here's where you've got to be able to apply the rules within functions. That's very, very good, okay? 1 over x, as x gets huge, what is 1 over x going to approach?
0.
It's going to approach 0, okay? So, now, you do have this exponent that's getting bigger and bigger and bigger, okay? But, because this is approaching 0, the inside of the parentheses is approaching 1, and like Hugh said, 1 to the 100th power, 1 to 1,000th power, 1 to the 1,000,000th power, 1 to any power just equals 1. Okay? So, very good.
That was
Pretty cool, huh?
yeah.
Alright?
你们还没
Alright.
Pretty dope.
Now, just to tie things together, some of the things we've learned in the past that we're using here. Remember your leading coefficient test, okay? If your leading coefficient is positive, it increases to the right. If the leading coefficient is negative, it decreases to the right. If the degree is even, then the left and right side are going to do the same thing. It's either going to go up and up or down and down. And if the degree is odd, then the left side is going to do the opposite of the right side. Okay? So, you know, if you have a plus x cubed, it's going to go like this. If you have a minus x cubed, it's going to go like this. However, if you've got an x to the 4th, if it's a positive x to the 4th, it's going to do some stuff in the middle, but it's going to go up on both ends. And if you have a minus x to the 4th, it'll do some stuff in the middle, but it's going to go down on both ends. Okay? That's stuff we learned back in chapter 2, but it applies here. It can help us as we determine, you know, if we're approaching positive infinity, but this one's going to go up, this one's going to go down. If we're approaching negative infinity, okay, same thing. But if the degree is odd, it's going to be different. Okay, so you have to pay attention to that. The other thing we already pointed out is the relationship of these horizontal asymptotes to the limits as x is approaching infinity or negative infinity. Okay? Alright, so we're going to take some time. There's some that's a little bit of matching. Okay? Here, it's really just using, oh wait.
Yes.
Okay, yeah, there's A through G, or A through H. Alright? You're matching this with its graph, but it's kind of, again, kind of reviewing that horizontal asymptote idea. And then here are a number of limits that we can find using the rules that we just learned. Alright? So at this point, I'm going to stop the video and want you guys to work together to try to get some good practice using these limits and using the rules for them. Okay?